Hi everybody, I'm Jim White. You may not know about it, but the Earth's magnetic field is getting weaker and it's moving from northern Canada towards Siberia. And it's moving and weakening at an unprecedented rate. And I've included some links to videos about this under the Show More tab. I've been working on a device for measuring the Earth's magnetic field and direction, and you can track it yourself if you're so inclined. The measuring circuit uses a Hall effect device to actually measure the magnitude and direction of the magnetic field. I'll show you the circuit for that, and then we'll test it out and see if it really works. Now here's a Hall effect device that I came across that will put out 9 millivolts per Gauss, plus or minus 3%. And here's what it actually looks like, if I can get it to focus, compared to a paper clip. It's roughly 3 millimeters by 4 millimeters and 1.5 millimeters thick. There's the pin out, and normally it'll take up to 8 volts, but normally it's designed for 5 volts. At zero field strength, it puts out 2.5 volts. So, and then that voltage goes positive for a north field and negative for a south field. And you can easily saturate this device with normal magnets. The same family of Hall effect devices has various sensitivities. There is one that is only 0.5 millivolt per Gauss, which would be more useful for measuring fields around magnets. But 9 millivolts per Gauss made me think about, well, can I measure the Earth's magnetic field with that? Now, it turns out in my location, the strength of the Earth's magnetic field is around 53,000 nanoteslas, which is roughly half a Gauss. So at 9 millivolts per Gauss, I could get 4.5 millivolts from the Earth's magnetic field. And of course, that could easily be amplified. Now at my location, there's something called the inclination. The Earth's magnetic field actually points downward at 68.5 degrees. Now at the North Pole, the inclination angle is 90 degrees. It points straight down. So that's another interesting thing that we can measure with the Hall effect device. Now here's the circuit that I used. And I use the old NEMA symbol for resistors. Today it's the zigzag thing. But at any rate, I think it's obvious those are resistors. Now I use a 9-volt battery and an LED to tell me when it's on or off, and then a voltage regulator to drop that down to 5 volts. Now the LM78 is capable of 100 milliamps output. And you see the pin numbers there. And here's the pin out for the LM78. Then an important part of using this Hall device is the zeroing of it. To get a zero output signal, we need to match that 2.5 volt output from the device, and there's some variability on that output. So here's a circuit to make it easy to do a very fine adjustment. That's actually a 25-turn pot. Now all these parts are listed under the with links under the Show More tab. So I'll take you to the breadboard now and show you how things work. Here is the breadboard of the circuit that I drew previously. It's just a piece of wood with brightly finished finishing nails forced in to become the nodes of the circuit. Don't laugh, this is a very practical way to make a breadboard, because you can screw on large components, you can write on it, and you can lay it out in the form of the circuit so it's easy to troubleshoot. Now I have a Hall effect device way out here on the end of a wire so that we can probe around some magnets to show you the intensity of various types of magnets. Now in this case I have the meter set to volts because we can get full output with some of these magnets. Now here's some fairly weak ceramic magnets, and let me get the meter in the picture if we can. Okay, as I approach the magnet, nothing happens because we're not turned on. If all else fails, turn it on. Okay. Now as I approach the magnet, you can see the voltage increasing. And there's 0.8, well, it's minus 0.8 volts. If I rotate the sensor over, we go positive 0.8 volts. And there should be a magic spot where I hold it vertical edgewise where we can get close to 0 volts because the magnetic field is going past the device rather than through it. Now here's a piece of magnetite that I got at a gem show. Let's see what kind of a field this gives us. Reading 0.8 volts, which is about the same as these weak ceramic magnets. Now here's a stronger ceramic magnet, and there we're reading 1.3 volts. And if we turn it over, it'll read negative from what it was reading before. Okay, there's 1.3 volts, and there's minus 1.3 volts. Now with a much stronger little magnet, this is just two little magnets stuck on a piece of steel, but they're very strong magnets. So as I approach that, we go all the way to 2.5 volts, which is the maximum we can get out of the circuit. It can go plus or minus 2.5 volts. Now this particular Hall effect sensor is 1.3 millivolts per Gauss. And we're going to switch over to a 9 millivolts per Gauss to try and measure the Earth's magnetic field. Now, right now I'm in a metal building with a metal roof. So the Earth's magnetic field is kind of screwed up here. And what we're going to have to do is I have a ham shack in an outbuilding, and we can go out there where we won't have all the effects of a metal building. Now, to do our tests out there, I made this little thing which we can hook up to our breadboard here. And the Hall effect sensor is glued right there to the end of the board. The blue stuff is from a rubber band that held it in place while the glue was setting up. And so I now know Elmer's glue all, which is similar to Gorilla Glue, adheres very nicely to rubber, because I had a heck of a time getting it off of there. Now this appendage on the back here is just to make it easy to see the direction that the sensor is facing. So when we go out to the ham shack, we're going to try and find north and south and the angle of inclination of the magnetic field. Okay, here we are in the ham shack, and I want to show you this map. This is what's called an azimuthal map, or a great circle map. And it's ham radio operators use it to determine which way to point their antenna for various countries. And I hope you can see the pointer there. For instance, India is essentially due north. And the southern areas of Africa would be due west. Due east. And Australia would be due west. So you learn a little bit about the globe with this type of map. Now, there's two dots here. This one is where the North Pole was in the year 2000, and this is where it is today, if I did it correctly. Now for me, I'm located in this area. It's essentially moving away from me. Now if you're located in Europe, and you were facing north, it would be moving from left to right. And if you were located in Australia and looking north, it would be moving from right to left. So for me, the biggest change would be the angle of inclination would be changing much more than the right to left angle. But depending on your location, things would be different. Like in Europe, the angle of inclination is probably not changing very much, but the pointing direction is. Okay, here's our setup. Here's the breadboard. This time I turned it on. And here's a compass showing where north is. And here's our meter. And this time it's on the millivolt scale, because we're going to be looking at much weaker magnetic fields. And then here's the pointing stick that I described before. Now, if I get this lined up where that top cross arm is pointing east and west, right there we have a zero signal because the field is passing by the sensor rather than through it. Now, if I can keep everything level and turn this to north, we see 1.7 millivolts. Now the plus or minus is just how I hooked up the meter, so everything's relative here. Now if I swing around 180 degrees, you see the signal goes positive. Now, I'm trying to hold it level. Let's come back around to north. And I'm going to start tilting it towards myself. And you can see the value is going up. Let me get off to the side here. So the angle of inclination here is about 68 degrees. So we reach a maximum at that point, and if we keep going, it should get weaker. I can't keep everything in the frame here. There, finally it started to drop. Now, even at that angle, if I turn it and line up east and west again, you see the signal goes to zero again. So there we have a demonstration of the pointing angle as well as the inclination angle. And we can detect both with this particular sensor that's 9 millivolts per Gauss output. Now, to go into a computer or a data acquisition system, you might need an amplifier to amplify the signal. If you wanted to actually track the magnetic North Pole, either the pointing angle or the angle of inclination over time, you could easily feed it into an analog input of a microprocessor and mount the sensor very rigidly somewhere, and possibly mount multiple sensors at very slightly different angles and watch how things would change from one sensor to the next. So there's a lot of ways to do it, but you'd probably need to amplify the signal to get a decent resolution. Now here's an interesting point. If I bring the sensor near the compass, I'm above the north part of the needle, you notice the output signal is positive. And if I move it to over the south end of the needle, it goes negative. And when I line it up pointing towards the North Pole, it's negative. So that says the North Magnetic Pole is a South Pole, which I never thought of before. Well, there you have it. There's a very simple circuit you can use to play with Hall effect sensors. And I don't know if I mentioned it, but these things are only about $2 a piece. I started into playing with the Hall effect sensors because I wanted to make a DC meter, ammeter, for measuring currents of metallic thermocouples. And I'm going to keep going with that. And I think the next video will be about thermocouples and trying to use them to generate power, and the semiconductor type thermoelectric generators as well. So I hope to have that out soon.